In this section, we're going to start working with products of radicals. So more so with the radical stuff and changing it to exponential form. That means we're going to have an exponent. So 8.5, the question is, how do I multiply and simplify expressions, specifically using radicals, and we're also going to use the rational exponents. So we'll practice multiplying them together and simplifying different rational exponents and radical symbols. We've done a lot of square roots before of different numbers, say like 80, and then some letters in there, maybe like, a to the fourth, whatever. We're going to do this as well with some other numbers that are in the index, which is this part right here. The index number will be something like 3, like the cube root of this. So we're going to be changing it up a little bit and changing this number here when we talk about radicals. So we have a couple properties to go through. This is kind of an old one that we've used before. The first property of nth roots is that if you have the square root of a times b, as long as a and b are not negative numbers, then you're allowed to break them apart into the square root of a times the square root of b. We've done this many times before. We showed an example of how this works. So this is just kind of an old thing we've done, which we're going to use again. Then we're going to use this property. It's kind of the same idea, but we're going to start it out as the ab to the 1/2 power. So if you remember that this is actually the same thing as this, right? If you have the square root of ab, that means it's the same thing as ab to the 1/2. So you can also do the same thing, which in this case, the 1/2 goes to the a and the b. So you could write it as a to the 1/2 times b to the 1/2. Which also is the same thing as up here. Right, these are all the same thing, it's just written differently. Here's the radical version, these are radicals. Specifically, these are square roots. And here you have rational exponents. So, for example, we're going to try this property out, see what it's like, and how it works. We're going to simplify both sides of the following equation to see if this property holds true. So on the left-hand side, we have 4 times 49 raised to the 1/2 power. So first, we're going to do the left-hand side over here where we multiply the numbers together. So let's do 4 times 49. And that would give you 196 to the 1/2 power. This side you could also do. I'm just going to stick with the left-hand side for right now. Now, 196 to the 1/2 power is the same thing as saying the square root of 196. Which happens to be the number 14. All right, now we're going to work on the right-hand side. So what happens if we break these into two separate ones, right? The 1/2 went to both of these. We can do the 4 to the 1/2. And if you don't know how to do these in your head, you can use a calculator. You could also use the table, the exponent table. 4 to the 1/2 is 2. It's like saying the square root of 4. Times 49 to the 1/2 is 7. And then 2 times 7 gives you 14. So this property does work, and it's usually best to have non-negative numbers. So positive numbers work the best here. Okay. So in general, we can say this about any root. We don't have to be talking about square roots. So for any non-negative real numbers x and y, so non-negative, talking about positive, and any integer n is greater than or equal to 2. So the number that's in here in the index has to be bigger than or equal to 2. You talk about square roots, the cube roots, fourth roots, and so on. In the power form with an exponent, you can just put the 1 over n to everything. So it's the same idea. So we can write this out as x to the 1 over n, and also y to the 1 over n. It doesn't really matter what number is on the bottom. The last one that we did back here, it was 1/2. But we can have any number in the denominator here. It's 1 over whatever, as long as it's bigger than or equal to 2. And then the next property would be the same idea. The nth root of xy would be split them apart, nth root of x times the nth root of y. So this is the more general property, because you can have any numbers here for n, and x and y's have to be positive. So for our first example, we're going to calculate the cube root of 50 times the cube root of 20 without a calculator. So this is where you would actually use the exponent table. if you need it. And note, first off, in order to use this property, just to be clear, you have to have the index of each one has to be the same. So the index must be the same. So if you're looking at the index on both of these, that's these numbers right here, the 3 and the 3. If they're the same, then you can actually use these properties up here, right? Because when you have this number here or here, they got to split into to be the same thing. So we're actually going to use the backwards version of this. We're going to start with this and work our way back to this. So if we have the cube root of 50 times the cube root of 20, that's the same thing as saying the cube root of 50 times 20. Now the whole reason of putting these together is because by themselves, you really can't do a cube root. 50 is not a nice cube root, and neither is 20. However, if we put them together into one cube root and multiply them together, do 50 times 20, you end up getting 1,000. And we do know the cube root of 1,000. That is 10. So by themselves, they're not much of anything. It can be decimals, right? But once you put them together into one root, you can actually solve it out. So the cube root of 1,000 is 10. Or you can write this as 1,000 to the 1/3 power. Also 10. That's our answer. All right, let's throw some variables in there. We're going to assume that our variable is a positive number. Perform the multiplication. So we're going to multiply these two together like we did before. They're both 4, so that's perfect. So we're going to have the 4th root of 5x times 125x to the 3rd. Okay, so I'm going to work in here, put this stuff together, and then we'll deal with the 4th root. So this is the 4th root of, we have 5 times 125. That would happen to be 625. And then we have x to the 1st times x to the 3rd. This is when you would add the exponents to get 4. So I'm going to do this a little bit differently here. Now we're going to split this apart into the 4th root of 625 times the 4th root of x to the 4th. So we kind of like combine them first, and now I'm splitting them back apart after we were able to actually put the numbers and the variables together. Then we just do these individually. That is on the exponent table. I believe that is the number 5. And then over here, the 4th root of x to the 4th, well, these numbers match up. They're actually going to cross each other out, and you just get x. So the answer is 5x, no roots anymore. Now, this doesn't always happen. If these numbers don't match, we have more of a problem, more of an issue to go through, which we'll see at some point. But for now, it's nice and easy, 5x. So now we're going to try to simplify some radicals that aren't very nice as far as they don't work nicely in the table, in the exponent table. So we're going to simplify this into the radical into its simplest form. So before we did this with square roots where we broke it into two different numbers where one has to be a perfect square. But now we're going to break it into one of them has to be a perfect cube, right? So your cubes are like 1, 9, 1, 8, because that's 2 times 2 times 2. 3 times 3 times 3 would be 27, right? 4 times 4 times 4, that's 64. So we're trying to find that. So if you had the exponent table, you would look at the x cubed row or column and go down those numbers. I think it goes 1, 8, 27, 64, dot, 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 dot. And we're going to figure out what number goes into 240. So we can break this into two different numbers. So that way we can simplify this a little better. So I would just take these numbers here and we start dividing them by 240. So let's try something. We do 240 divided by 8. That happens to be the number 30. Right? So if we do 240 divided by 8, I just picked that one at random. You get 30. Ah, that must mean these two numbers work. If you tried another one, let's see, what's 240 divided by like 27? 8.8 repeating. Nope. 240 divided by 64. That's 3.75. So I don't think any of these other ones work besides 8. So we're going to break this apart into 8 times 30. And so let's go ahead and write it that way. So we have the cube root of 8 times 30, which I'm going to use that property where we can break it apart and say this is the cube root of 8 times the cube root of 30. And we know the cube root of 8, which is the whole reason why we use this. So if you use the table, you go down and you look across to the left, and that is the number 2. This is 2 times the cube root of 30. Now you have to be really careful here because that 3 is an index, so it's kind of sitting inside the root symbol. Don't make it big and sit it out near the 2. The 2 is a big number, and it's on the same level as the 30. So one question would be, like, could you go further with 30, right? Could you break apart 30? The problem is you won't find a perfect cube in 30 because 30 is like 3 times 10, right? And 10 is 2 times 5. Like, we have 3, 2, and 5. Like, that's all we have. Nothing else can go perfectly into a cube root. So that's our answer. I have 2 more. Okay. Example 5. Suppose r is greater than or equal to 0 and s is greater than or equal to 0. So we're saying these are positive numbers. Simplify the following expressions. Alrighty. So what I'm going to do is I think I'm just going to separate all of these into 3 separate ones. So we have the cube root of 64 times the cube root, of r to the 6th times the cube root of s to the 15th. Okay, that doesn't look that good. This binomial thing does not work out so well for me. S 15. So we're going to do all these separately. The cube root of 64, and actually, if it's easier, you might want to change this to the exponential form, and I might do that for these last 2. But remember, this is the same thing as 64 to the 1/3. So you could use your chart for that. We can do that for all of these. This would be r to the 6/3. This is what we used yesterday, this property, times s to the 15/3, right? And then we just simplify all these individually. This, in the chart, if you look at it, is the number 4, I think. Yep. This would simplify to r. 6 divided by 3 is 2, so r squared. And then 15 divided by 3 on the s would be 5. And that would be your answer. So if you kind of go back to this, you can kind of ask yourself, instead of writing it like this every time, what you're really doing is saying, how many times does 3 go into 6? 2 times. How many times does 3 go into 15? 5 times. And that's your answer. Now, it is possible that you don't get something as nice. Like, what if 3, when it was trying to go into like a number like 7, that's a lot, like way more ugly of a problem. We're going to try something like that. That's our last example. Then I might do some huddle ones. I don't know. This seems to be pretty short. Suppose x is greater than or equal to 0. Simplify, and we're going to rewrite the cube root of 120x to the 4th. We're going to use a smaller power of x inside the radical. Okay, so we have a couple things going on. We have 120. That is not on the table, unfortunately. So we have to break apart 120. And then I'm also going to break this into the x to the 4th by itself. But first, let's figure out how we can multiply to 120. So let's try the 8 one again. So if I do 120 divided by 8, I'm just going to do 8 because that looks like a good number to use. And why am I using 8? Because we're looking at perfect cubes, not perfect squares. And that actually gives you 15. Okay, so we're going to use 8 and 15. 8 times 15 is 120. So I'm going to break this into 3 separate ones. We have the cube root of 8 times the cube root of 15 times the cube root of x to the 4th. Like so. Now this one's going to get a little bit more tricky here. Cube root of 8, you could also write as 8 to the 1/3. Use the table. This one will not simplify at all. So we're going to have to keep the cube root of 15 the way it is. Whether or not you make it like this or raise it as an exponential, like a fraction exponent, that's okay too. So this one we can do. We would get 2 times the cube root of 15. This one we would have to maybe rewrite and think about it that way. So we're going to do x to the 4/3. Now, we haven't done something like this before, so it's going to be a little different. Let's just talk about this one, x to the 4/3. How could you simplify this? Well, it is improper fraction because 4 is bigger than 3. So you just ask yourself, okay, so how many times does 3 go into 4? That's 1 time. So you could write that as x to the first, and then what do we have left? We would have 3 goes into 4 1 time with 1 left over. We would have 1/3 left over. So let me go through that again. So you're saying how many times does 3 go into 4? 1 time. Okay. And then how many are left over if it goes into 4? It would be 1/3. So if you actually put these together, you would actually get 4/3. And then I'm just going to copy the rest of this down. Cube root of 15 times 2. So we got a lot of junk to mess with here. Okay, so this cube root of 15 is the same thing as having this, because this is also the cube root of x. So I'm going to put them back together, and I'm going to put these two together. Since there's no roots here, we have 2. This is an x to the first. And then this is the cube root of 15. Whoops, let me just rewrite that. Cube root of 15. And this is also the cube root of x, right? This is the same thing as cube root of x. Put them back together, we get this. And that's our answer. It gets a little bit more difficult as you go through these, right? There's a lot of things going on as far as breaking them apart, and the variables get a little difficult. So there's a lot of things to kind of remember to go through these. So I think I'd like to do maybe some more. This one seems, that was not bad. How about something like this one here? Suppose w is greater than or equal to 0. We're going to rewrite this as a smaller power of w inside the radical. So we're going to rewrite this as w to the 17/5, right? So you're going to ask yourself, how many times does 5 go into 17, right? So that is 5, 10, 15. It goes in there 3 times. So we're going to have w to the 3rd. We're trying to figure out our new exponent, times whatever is left out of 5. So 5, 10, 15, we get up to 15, and that means there's 2 left, so we have 2/5. The w to the 3rd is just, that's what it is, right? Times this you can rewrite as a radical. So we're going to rewrite this as what? This is the bottom number. It changes to 5th root. And then the top number we can write inside with the w squared. So this would be your answer. I don't think there's an easier way to do it. Like that's it. If you wanted to keep this as a radical the whole time, oh boy. So you do this problem the same way without going to exponential form. You would do the same thing. Like how many times does 5 go into 17, right? So that's 3 times. So you would write w to the 3rd. And that takes you up to 15, so there's 2 left over. So we'd leave a 2 left in there with a 5. I don't know if this is better or worse, but either way, you get the same answer if you don't like dealing with this. Is there any more like that? These ones are easy. These ones are better. This one looks good. Cube root. We're doing a lot of cube roots, huh? Let's maybe do a 5th root one real quick. So you have 96. That's not a nice perfect 5th root. You would have to go down your 5th root column, right, on your table and see what would work. Let's see. We have 1. Obviously, it's not going to work. Then we have like 2 to the 5th, which is 32. Does that work? 96 divided by 32? That does work. So we did 96 divided by 32. You get 3. Okay, so we want to break this into 32 times 3. So we're trying to find perfect 5th roots. So we would have the 5th root of 32 times the 5th root of 3, and I'll also break this variable up too. We'll change that to times the 5th root of y to the 11th. This part you can use in the table. 32 to the 1/5, that's the number 2. This will stay the same. We have the 5th root of 3. And then this one we just have to simplify. 5th root of y 11th. If you'd rather do it this way, you could do that. Basically what you're asking yourself is, how many times does 5 go into 11? And that would be 2 times, okay? So we have 2, and 5 goes into 11 2 times to get up to 10. So 2 times. And then there'd be 1 left over. All right, so we have times the 5th root of 3 times y to the 1/5, which is the same thing as the 5th root. So I would write this as 2y squared times the 5th root of 3, and then this would also be in there because you could rewrite this as 5th root of y, so it'd be 3y. I know these ones are tough, that's why I'm trying to do some extra ones for you and with you. I'm going to do one more before we wrap it up. This seems like a decent one, maybe. 640. We're trying to find perfect cube root. Well, 64 is a perfect cube, right? So we go 64 times 10. I think we do that, right? 64 times 10. 64 is a perfect cube root, if you look on your table, down the x to the third column. And then we'll break the rest of this apart. So we have the cube root of 64 times the cube root of 10 times the cube root of, x to the 12th times y to the 11th. I'm just going to keep them together for now. So let's simplify this. This would end up being 4, right? That's what that simplifies to. This is not going to simplify at all, so you might as well just keep the 10 in there with the cube root, because that's going to kind of go back together. So we're going to have, I'm going to leave some space here. We're going to have the cube root of 10, and now we're going to talk about the x's. So what you're essentially doing every time is you're asking yourself, how many times does 3 go into 12? So 3, 6, 9, 12, that would be 4 times. So that's what comes on the outside, x to the 4th. It goes into it perfectly, so there is no leftovers inside here. So that's part of the answer here. Now we're done with the x's. They do the same thing with the y's. How many times does 3 go into 11? Right, 3, 6, 9. And if you go to the next one, you get 12. So we just know it goes into there 1, 2, 3. So there's 3 y's. And how many would be left over if you went up to 9? There would be 2 y squared. And that's actually your answer. You have 4x to the 4th, y to the 3rd, times the cube root of 10y squared. All right, one more. 1250. Ooh. I'm going to have to probably use the table for that one because I don't know what that would be. Is it 625 times 2? I think so. So this will break apart into 625 times 2. Yeah. All right, so we're going to do the 4th root of 625. Use the table. Times the 4th root of, I'll keep the 2 in there. And we might as well keep these in here. Y to the 3rd, and p to the 17th. Okay, this part we know how to do. 6 root of 625 would be 5 times, I'm going to leave some space here. We have the 4th root of, 2 is going to stay in there. Then you ask yourself, how many times does 4 go into 3? Well, that's not possible. 4 does not go into 3. There's not enough. You have to have a higher than a 4 or higher to actually take anything out. So this y to the 3rd is going to stay exactly where it's at. Then, how many times does 4 go into 17? That would be 4, 8, 12, 16. Can't go any higher than that. So 1, 2, 3, there's 4 of them. So we're going to take out p to the 4th, because there's 4 sets of 4. And since we got up to 16, we're 1 over, or 1 left, so p to the 1st. And that would be your answer. These ones do get kind of complicated, but I wanted to go through a bunch of the huddle so you know how to do it. Might as well do another one. Why not? How about this one? The cube root of both of these. That's the same thing as doing the cube root of y to the 25th over the cube root of 8. So the cube root of 8 is on the table. You can look at that. That gives you 2. This one we're asking, how many times does 3 go into 25? So you can get up to 24, right? 3, 6, 9, 12, 15, 18, 21, 24. That would be 8 of them. So you can take out 8 sets of 3 times the cube root. If we're up to 24, there's 1 left. So it'd be like that. And that would be your answer. So that will finish up this lesson. I did most of the huddle with you, and you can finish up the rest of the mastery and huddle. That's the rest for 8.5.